Okay, I want to start by reviewing some things that we already know about electric charges, and that is that if I start off with, if I have two electric charges, let's say a positive or a negative charge, then there is going to be an electric field established between these two, or even just one charge has an electric field. But if I have a positive and a negative charge, there is going to be a force involved between these two. And so we're going to call this positive charge, charge A, and this negative charge, charge B. And I want to go ahead and just talk about, well, what is happening to this force? Well, the negative charge here is going to be attracted to charge A, and charge A, the positive charge, is actually going to be attracted to charge B. And so there is a force. We're going to call this the force on A by B. We'll call this the force on B by A. And they are attractive forces, which means they go towards each other and they point in opposite directions. Now, I want to go ahead and make a convention here. We're going to say that that anything that points away from a positive charge is going to be a positive direction. And anything that points towards the negative charge is going to be in the negative direction. This is just for simplicity of a two-dimensional model. As we know and what we've seen before is if I had another charge here, then our directions would actually have to be a little bit more in depth with an angle. But for this one, this will suffice. And so I can say that this force by B on A is actually going to be a negative force, and the force on charge A by charge B is actually going to be a positive force. Now that's important when we start talking about, well, the force equation, which is the electric force equals, I don't know why I keep putting a T there, equals Coulomb's constant times, in this case, charge A times the charge on charge B divided by the distance between them squared. Okay, so this is the equation we got last time. And now I want to go ahead and take this further. We're going to start talking about the energy associated with this type of problem. Now, one thing we know is that that anytime we have a force involved and charges or any object is allowed to move, then we have what's known as work. And so just to redefine work, it is a transfer of energy to an object by a force that causes a displacement. Okay, and we've seen this before in a field force before, and that's gravity. And so if I have a block here sitting on the ground, and I apply a force pointing up, and we'll call that force F, and the block moves a displacement of D, then the work done was force times displacement. And in this case, the work equals the gravitational potential energy. Okay, and we've talked about potential energy before and gravitational potential energy. And so we know that the work equals the gravitational potential energy. Well, the same thing is going to happen in an electric field, where the work in an electric field is going to equal what's called the electric potential energy. And we have a special name for that, and we'll get to it later. So the work in the electric field equals the electric potential energy. So let's talk about this. We know the equation for work is force times distance. And so our force in an electric field is gotten by, well, we said that it was this equation, but we also had a simplified version where the force in the electric field was the electric field strength, E, times the charge. And so in this case, let's say that charge A is stationary and charge B is allowed to move. Then the force is the electric field, E times the charge B, and then we want to times that by the distance. Now E, well, let's go back here to the QA, QB all over R squared. And if I multiply that by the distance, well, the distance between these two is, well, that's R, right? So in this case, this would be the force required or the work required to move this charge from being right next to the positive charge out here to being at its location 1 R away. And so D will equal R, and I'll get this equation right here. But if you notice, I have an R on top, so this is the same thing as R over 1, and I have two R's on the bottom, and so these will actually cancel. And I'm going to get that the work on or on charge B by charge A. So the work that charge A does to charge B is equal to K, the charge of A, times the charge of B, all over R. Okay, so that's a work equation. Now, what we like to do is we like to make our work equation or our work number charge independent, and that's called voltage. And so we've seen this term before, voltage. Voltage is just work that is charge independent. So I'm going to divide off the charge of B. And so basically we're saying, well, this is just going to be 1. And then so this is going to equal the amount of energy required to move 1 coulomb of charge. And so this will be, the units for this is joules over coulomb, and that equals volts. All right, so let me show you what this means. It means that if I were to take the work equation here, and I wanted to know per unit charge what my energy is going to be, well, I will divide both sides by the charge that I'm moving. Okay, so I'll divide that over here, and I get that the voltage now equals work divided by the charge of B, which also equals K, my original charge, the charge that's being my reference for my electric field, divided by R. Or I could say that the voltage times the charge that we're moving into the electric field equals the work. So this is the work required to move a certain charge inside an electric field with a voltage of V. And so this is another equation. So let's talk about if I have a 12-volt electric field. So that equals the electric field strength. Electric strength. Okay. And that's not really quite right in the fact that KQA over R is the electric field strength. And so, yeah, over R squared is the electric field strength. But I'll just use that term right now. But I have 12 volts. I have 12 volts of an electric field in a certain spot. So here's a positive charge. Let's say right here is an electric potential energy or electric potential of 12 volts. Okay, so at this distance away from my positive charge, I have 12 volts. So if I measured that, I got 12 volts. Well, that means that at this point, if I had 1 coulomb of charge, so if my charge equals 1 coulomb, well then it will do 12 joules of work. So it has an energy or an electric potential energy of 12 joules. If I had a half of a coulomb, though, of charge, well, then it has an electric potential energy of only 6 joules. All right, and that's because 1/2 times my voltage, which is 12, gives me 6 joules. Okay, so this is electric potential energy, which is the work given by this equation over here. Let me erase this and fix this so that we got a right equation. QB. Okay, so the work or the electric potential energy, so they'll call this PE electric. And then we want to take that energy and we want to turn it into a per unit charge, so it's charge independent. And so we divide the charge of particle B from it and we get volts or voltage. Okay. Now volts is measured in volts, and which is also given the symbol V. So just make sure that you have V. Anytime you see this capital V, it stands for voltage. Okay, now we're going to move on. We're going to talk about circuits. There are 3 major parts to every circuit. Okay, and I want to talk about those. You have the voltage source. Now the voltage source gives the electric potential to, it gives the electric potential to the electrons or to the charges in the circuit, and that's what causes the electricity to move. All right, we'll talk a little bit more about what electricity is, but right now every circuit has a voltage source, and most often this is called a battery. We just have a battery. Another thing is another major part is a conductor or a wire. So wires or some kind of conductive material. Okay, and the whole function of wires or conductive material is to transfer the electric field through the circuit. Okay, the electric field, I probably should have spelled that out, but the electric field throughout the circuit. And so this is also allowing the voltage to move throughout the circuit. And then the last thing is the load. Now we call it the load, but actually it is the device that is being powered in the circuit. C-U-I-T. I keep hitting the wrong button. Okay, so we have the load, we have wires, and we have voltage source, or a battery. Now, if I were to draw these, I'll just do this real quick. I start with the symbol for a battery, and so this is the symbol for a battery. And whenever you draw symbols, there's actually only certain places that you can actually touch wires to. So a battery looks like this, and whenever I draw symbols on it or wires attaching to it, I will attach them to these spots that I'm circling in red. Those are called contact points, and those are the only places that wires can attach to devices, or contact points. And so a wire is just a straight line, so if I were to draw a wire off of this, it would look something like this. And so here's some wires. All right. Now a load, for our intents and purposes right now, we're just going to draw a box. So this is the device that we want to run. So this could be a motor, this could be a light bulb, this could be a speaker, this could be anything. So we have a battery and we have a load. Now a battery has some very important parts about it. As we all know, batteries have a positive side and a negative side. So if I were to draw an actual battery, let's see how good I'm at doing at this. Okay, so here's like a AA battery. Well, I have a positive side, which is the side with a little nub on it, the little bump on it. And then I have the negative side, which is the flat side. And we should all know this. So this is a big AA. Now, we know the names of these as being positive and negative as far as the ends go, but they actually have a very specific name. The positive side is called the cathode. And the way I remember that is that cats are awesome, sure, if you want to believe that. And so they're positive. Okay, so the cathode of a battery is the positive side. The negative side of the battery is called the anode. Okay, so the negative side over here of this battery is the anode, the positive side is the cathode. And we'll need to know those more specifically when we talk about in the next video, current, because we will use that to reference a lot of things. So cathode is the positive side of the battery, anode is the negative side of the battery, and there's a third part to a battery, and that is on the inside. And on the inside, I'll just draw it like this. Let's pick it blue. There's a liquid. Now, it's not really blue, but it, just so that we're making colors. There's a liquid called an electrolyte. Now, the electrolyte has a very important function. What it does is it separates positive and negative charges. And this is through a chemical reaction. So through chemical reactions. Okay. So it separates positive and negative charges through a chemical reaction. And what it does is it takes the positive charges and it moves them over to the cathode. So we get positive charges that hang out on this side of the battery. And then we have negative charges that hang out on this side of the battery. Now, one thing about this is that normally they'd be attracted to each other and they want to recombine. But the battery and the electrolyte does not allow them to do that. So there's like a barrier here. So what this does is it leaves positive charges over here on this side and negative charges on here. And there's only one way for them to get back to recombine, and that is through our circuit. And so the wires transfer them through our circuit, through our load, and then back to the positive side of the battery as far as the negative charges go.